All right, our last speaker is Shravan, who is also from the APFL.
Hi, everyone. Can you hear me? Yeah. Okay, so I'm also from EPFL, but not from the same lab as Behrad, but from BioRob. So today I'm going to be presenting about neuromuscular modeling approach to study mammalian locomotion. Like the previous speakers spoke about sensory motor integration, it's really important and vital to study locomotion. But one of the biggest challenges in doing that with real animals is that it is so complex, like as I show the interaction in the most simplest form here, to study the interactions of all of these components together in animals can be quite challenging. A powerful solution can be to use simulation models, like where you have an environment to study each of these individual blocks, individual components, and also the interactions between them dynamically for different types of locomotion activities. While you wonder, like there are so many platforms available for robotics to do the same kind of studies, one of the biggest missing components and surprising things for me is that we don't have such extensive tools or frameworks to do it for animal locomotion. Like probably the only thing I can think of is like OpenSim, but it is still limited to biomechanics, but not like the whole locomotion components itself. So one good thing is like the Human Brain Project is working on like developing the neurorobotics platform, trying to integrate all of these open source tools together to perform large-scale brain simulations that can be integrated with the bodies. In this talk, due to time constraints, I cannot go into like the features of this platform, but we have a demo session on Thursday. But what I'm going to talk about is like the first featured experiment that we are trying to model with the neurorobotics platform, that is the mouse or the rodent model, where we have like reconstructed brain models integrated with the spinal cord models and the musculoskeletal system. So as you know, all of these questions individually itself are like open and up for discussions. So we are also not only developing the platform, but also developing the science behind all of these components and how to integrate each of these systems together. And in today's talk, I will mainly focus on examples of spinal cord models and how I'm integrating them with musculoskeletal system to produce locomotion. So just to give you a background of the model, here you see like the mouse I'm going to use for the simulation results in the further slides. And you have like only hind limb locomotion right now, but we're quickly extending it to full body quadruped locomotion. Each of the hind limb consists of 4 degrees of freedom with the hip, knee, ankle, and the foot joints. And each of them have like at least one pair of antagonist muscles, which are modeled as hill type muscle models. So 3 examples that I'm going to discuss in this short time is like reflex controllers, CPG plus feedback controllers, and a much more realistic muscle spindle based feedback controllers. I label it as simple to complex, not in terms of difficulty in implementation, but how easily it can be relatable to the biological system itself. So the first one is the reflex controller. So here it's largely inspired by the work of Eckerberg and Pearson on cats. So basically, we're breaking a locomotion cycle into like 4 phases: swing, touchdown, stance, and liftoff. And the transition between each of these phases is governed by a reflex state. Like, for example, from swing to touchdown is based on when does a certain angle of hip and knee are satisfied, it gets a phase transition. As you can see here, like the phase transitions occur whenever a certain feedback rule is satisfied. So here is the first simulation example of the reflex controller. So as you can see, like we could produce, like with even simple rules, a stable gait cycle for the hind limb locomotion. And since it's a reflex model, you're strongly coupled with your environment. So here there's an example of the mouse walking downhill. And there's now an example of the mouse walking uphill, but with no change in parameters or no change in the control itself. So the biggest limitation of the reflex controller is the internal noises and the change in parameters for the model itself. So the next type of controller I discuss is like the work with Ilya Rybak's team. So here it's the CPG model that's along with the feedback circuits. So here it's much more biologically closer as we use circuits that are validated from the studies in the actual mouse model itself. So the neurons are modeled as like activity-based neurons or rate-based neurons with different types of feedbacks, 1A, 1B, and type 2. So here, again, a short example of the optimized network for like hind limb locomotion of the mouse. So I cannot go into the details of each of these, but you can talk to me later. And the final work that I'm going to show you is like the spiking neural network in collaboration with G-Lab. So here it's basically a work that was driven to understand or recreate epidural stimulation studies on mice and rats to reproduce locomotion after spinal cord injuries. So the basic overview still remains the same, connecting the spinal cord with the mechanics and the feedbacks. But the important part is the stimulation model. So here we wanted to recreate what happens in the actual mice, like where after a spinal cord injury, they lose locomotion ability, but still with stimulation on spinal cord, we can recover it. So since the spinal cord model was quite complex in this, we tried to simplify the biomechanics and rip the whole the body apart and just focused on one single joint, and we could reproduce with spinal cord stimulation oscillations in the foot. So right now we are extending the same model to the complete hind limb and in turn reproduce what we observe in the real animals. So in conclusion, like what we are trying to work towards is like have a complete biomechanical mouse model that's available for the community, and it's data driven. And so right now we can have we have examples of showing stable hind limb locomotion with different circuits being tested on the same model. So in future for next year, like what we aim for is like to have a brain and spinal cord integrated model driving the complete biomechanics. Yeah, thank you.
Yeah, a question or two for the speaker.
So you mentioned that this was a data-driven approach. Can you talk more about how you get the data? Is it in freely moving animals or is it in anesthetized animals? Because there's a lot of neuromodulation and like everything changes with if it's anesthetized or freely moving, right?
So it's a large-scale collaborative project with the EU. So that there are like different labs working on getting different types of data sets. So we have data sets at different scales, ranging from brain models to the spinal cord to the muscles. So I'm not exactly sure which one you're referring to. If it's referring to like the muscles or the biomechanics, then of course it's anesthetized and it's post the death of the mice, unfortunately. But like if it's something to do with like neural recordings, then we have during the locomotion itself. Which are not anesthetized, but it's healthy mice, and also after spinal cord injuries. So we have different data sets under different conditions.
Okay, this brings us to the end of the thing. Oh, thank you again.
Thank you.
Break till 4:15.
All right, this brings us to the end of the sensory motor section. We have achieved another coffee break, so